In this presentation, let's take a look at SOLIDWORKS Plastics, an injection molding simulation software completely embedded inside SOLIDWORKS that helps you predict and avoid injection molding manufacturing defects during the earlier stage of the part and mold design to avoid time-consuming and costly mold rework. We are looking at a smoke detector housing, and we will study more in detail the top cover. The first thing you might want to do inside of SOLIDWORKS is analyze this model for draft analysis. The draft is very important, and injection molding plastic parts require draft in order to be ejected properly out of the mold cavity. The nice draft analysis tool inside of SOLIDWORKS lets you quickly do that. Once you're satisfied with your draft analysis, we can move to SOLIDWORKS Plastic to optimize our plastic part design. After selecting the first configuration that we're going to look at, the initial step, like other simulation tools, is to mesh the model. Let's use what we call a surface mesher or shell mesh. We can specify the meshing parameters manually or decide to let the software mesh this cavity automatically. Some parameters, like the triangle size for example, can be set up by entering a specific dimension or by using the slider. We can also add some refinement to automatically use a smaller mesh for small features like ribs, holes, or higher curvatures areas. You have complete control over the density and the quality of the mesh. Once the mesh is created, we can go forward with setting up the rest of the boundary conditions. The next thing to do is to select the plastic material. SOLIDWORKS Plastic includes a very extensive plastic material database with over 4,000 grades of commercial plastics. For this initial analysis, we choose a grade of polycarbonate. Polycarbonate is a very good material with great impact resistance, strength, temperature resistance, and good insulation capabilities. It's an excellent potential candidate for this particular application. The last step before running the analysis is to specify the gate location or injection location. Let's just pick an edge gate at this point. After meshing the model, selecting a material and picking the gate location, we're ready to go and we can now run the analysis. After a pre-processing phase, you can see that the preview results are dynamically displayed on the screen as the analysis is being solved. It's an extremely useful feature since it allows you to see if something went wrong in the earlier stage. You can then stop the analysis, fix the problem, and restart another one. The Plastic Manager also provides some valuable feedback. You can know what percentage of the model is filled, the processing time, and what the maximum pressure requirements are. If you find out that the maximum injection pressure is starting to peak or is simply higher than the maximum pressure of the injection molding machine, you will know at this point that this part is unlikely to be manufactured properly without a design change, a process parameter, or maybe even a material change. As this analysis is running, the results are being generated. You can also see that we have a lot of different types of results that we're going to be able to look at. Not just the filling time plot, which can be seen on the screen, but things like the injection molding pressure, average temperature, flow front temperature, or cooling time. Our analysis is now complete, and we can look more closely at the results. But the first thing that comes up is what we called the result advisor. It basically explains all the different result plots and gives you some advice on how to troubleshoot and fix any potential problem. To gain further insight, we can animate the fill time plot. Here we are looking at the profile of the melted plastic as it travels in the mold cavity. One of the major problems that we have here is a phenomenon called racetrack effect. That's usually caused by a relatively thick wall section where the plastic in one area of the part rests ahead of the flow front in the rest of the part. It may or may not be a problem, but in this case, like in a lot of cases, it causes backfilling that create a lot of wet lines in these thin ribs. Wet lines are areas in your part where two or more flow fronts come together. It's going to be very critical from a structural standpoint, and it's definitely something we want to avoid. We can also look at some other results, such as air traps. These are places where the air that's inside the cavity gets pushed to. Other result plots also indicate a substantial cooling time of more than 60 seconds due to the thick area of this part. Now, using different configurations, we are going to analyze multiple variations for this part as we refine our design in order to find the best possible solution. In an effort to fix the racetrack problem, we decreased, in this configuration, the wall thickness in certain places of this part, especially around the perimeter. With the same injection location and material, you can see that we ended up with another problem. Because we decreased the thickness too much, we created a short-shot problem. No matter what you do, how you set up the machine, or how fast you inject the plastic, you just can't get the plastic to fill up 100% of the mold cavity. This moldy part would be nothing but defects. This new configuration features a slightly bigger wall thickness. You can see from just looking at the fill time plot that we can now fill 100% of this cavity without reaching the maximum injection pressure of a molding machine. The cooling time, which is the time it takes for the part to cool to a temperature for which it is safe to eject the part, is reduced significantly by more than 50%. It's because the wall thickness usually drives the cooling time, and the cooling time is often about 70% on average of the overall injection molding cycle time. This means that by improving the geometry of your model, you can reduce the cycle time and also lower the price per part. Now, even if the part is being filled correctly, we still have problems with the wet line being located in the middle of these thin ribs. In an effort to improve a wet line location, we change the gate location to another area of the part. The great thing about SOLIDWORKS Plastics is that you can run these multiple what-if scenarios to see what's going on and how to get the less amount of wet lines and best fitting pattern. At the end, it's quite an accomplishment. The new injection location definitely helped us reduce significantly the wet lines, and we now pretty much don't have any wet lines on those ribs. However, you can see that with 47 megapascal, our pressure to fill is still somehow high. We still need to get this lower, considering that we are looking at a single part cavity, and the injection pressure requirements will increase when moving to a multi-cavity mold configuration with sprues and a runner system. Let's make a material change. We started with straight polycarbonate and we are now switching to a polycarbonate ABS blend. It's very similar material in terms of properties and strength. Looking at our results, you can see that by switching to this new material, we managed to decrease by 20 to 25% the pressure required to fill the cavity, and that's going to help us to more easily manufacture this part. Being satisfied with this design and having overcome most of our initial challenges, we can also look at the volumetric shrinkage. All these plastic materials shrink. That's why the volumetric shrinkage at the end of the packing is more important. By changing packing pressure and time, we can actually affect what our volumetric shrinkage is. Overall, we reduce the volumetric shrinkage from the 10–12% range down to 1–2% range after packing. Also, we have a much more uniform distribution, with no significant differences from one end of the part to another, so it's highly unlikely that the part will warp or deform out of shape when it comes out of the mold. Now that we optimize our part for manufacturability, injection molding being a high-volume manufacturing process, we want to look at a multi-cavity family mold layout to mold the top and the bottom of the smoke detector housing in one shot. This ensures that all the parts have the exact same mechanical properties, density, tensile strength, chemical resistance, and even the same color and surface appearance. However, one of the problems is balancing the filling so that all the different cavities fill at the same time and at the same pressure. it's virtually impossible to figure out how to do that without the help of SOLIDWORKS Plastics. Within SOLIDWORKS Plastics, you can use runner balancing analysis tool and specify some parameters like the runner segments you want to vary. Then, the multi-iterative analysis will figure out what size those runners must be. Switching to the last configuration, you can see that the runner system was balanced and now all 4 cavities are filled approximately at the same time. In this quick presentation, we saw how you can use SOLIDWORKS Plastics to optimize your design and come up with the best possible solution. SOLIDWORKS Plastics is an invaluable tool for any mold or plastic part designers. Packed with many useful features and tools, including report capabilities to easily communicate your result to other members of your organization, SOLIDWORKS Plastics will help you ensure you more work the first time.